Good afternoon, everyone. I'm honored to present today. I'm Takumi Otagaki, a master student from University of Tokyo. I belong to Asahi Laboratory. The title of my presentation is Optimization of RNA Inverse Folding using the differentiable McCaskill algorithm and base pairing probability. I'd like to start by explaining RNA secondary structure. Unlike DNA, RNA typically forms base pairs within a single molecule, known as secondary structure. Here, I'll introduce the inverse folding problem. The goal of inverse folding is to find a sequence which falls into the target secondary structure with high probability. So why does inverse folding matter? It is essential for RNA design, which is critical in developing therapeutics and molecular synthesis. Okay, here I'll quickly introduce our contribution. We tried inverse folding using base pairing probability and also tackled pseudo-knotted structures. Here I'll explain about what is base pairing probability. It is the probability that I's and J's nucleotides form base pair. Below are examples of base pairing probability matrix. To calculate the base pairing probability, we use this equation. ZB, W, and Z can be calculated by McCaskill algorithm. This algorithm is based on dynamic programming. Here, I describe the sequence profile X. The sequence profile is position-weighted probability matrix like this, where I's vector indicates the probability of I's nucleotide in the sequence. For example, the probability of generating GCAG is like 0.5 times 0.2 and so on. Next, I'll explain the should expected value of base pairing probability, P star. It is defined as shown here. The expected value of dBij multiplied by wij divided by the expected value of the partial function z. A key point is this P star is differentiable with respect to the sequence profile X, meaning that it can be integrated into the automatic differentiation frameworks. This slide introduces our framework for inverse folding. In the figure on left, you can see that our model inputs the sequence profile X and computes the pseudo base pairing probability P star through differentiable McCaskill algorithm. And then we update the sequence profile X to make pseudo BPP matrix similar to the target structure matrix. Here, I'll introduce a previous related work, differentiable partition function. Matches and Kruger calculated the expected value of the partition function z. And they also calculated the should expected value of folding probability, as shown here. And they conducted inverse folding, optimizing the sequence profile X to increase this pseudo folding probability. Okay, my idea is based on this research. But so why optimizing pseudo BPP rather than pseudo folding probability? By making the pseudo BPP close to the target structure, our method considers an ensemble of structures around the target. Unlike the DPF method, which maximize only the target structure's folding probability, our method maximizes the total probability of nearby structures. Therefore, our method is expected to increase the chance of folding into similar structures and reduce the risk of folding into entirely different structures. Okay, I'd like to briefly introduce the dataset we used. First, we utilized structures from the Eternal 100 dataset with length of 50 nucleotides or less. Second, we selected random structures. We use structures randomly selected from pseudo base with its length around 50. Okay, now I'd like to explain the results of inverse folding on Eternal dataset. In this table here, DPF stands for the differentiable partial function. This is previous work. And answer 1 and answer 2 refer to the solution sequences provided by the Eternal dataset. And each cell value represents a folding probability of each sequence calculated by Vienna RNA package. Higher is better. Excuse me. As you can see from this table, we were able to successfully perform inverse folding on some problems. However, we were not able to outperform differentiable partial function. So these are examples. As you can see from this figure, these two examples show that our method successfully performed inverse folding. All right. Next, let me briefly explain about pseudo-knotted structures. Unlike ordinary structures, pseudo-knotted structures form not like base pairs, like these base pairs. And due to its complexity, it is very difficult to predict and perform inverse folding on pseudo-knotted structures. Okay, let's discuss the results of inverse folding on pseudo-knotted structure. We extracted 7 structures from pseudo base, and this column, target structure column, shows the target structures extracted from the database. This is the natural structure. Okay, and this optimized sequence column indicates the sequence optimized through our model. And next, the structure of optimized sequence displays the structure of optimized sequence predicted by RNA PK-plex in the Vienna RNA package. Lastly, this column presents the Hamming distance between the target structure and structure of optimized sequence. The smaller Hamming distance indicates the better results. Okay, and sorry. Okay, as you can see from this table, our model successfully performed on some targets. For example, with PKB ID 59, our model identified 2 sequences which falls into the target structure. Finally, let's move on to the discussion. We applied shared base pairing probability for inverse folding, and while our model was able to solve some problems, but however, it couldn't address all the problems in the Eternal dataset. And we guess the reason why the previous differentiable partial function method outperformed our method is that differentiable DPF optimizes the pseudo folding probability, which is more directly related to the actual folding probability. And next, our approach may be particularly useful for inverse folding on pseudo-knotted structures. The DPF method cannot handle pseudo-knotted structures because it's impossible to calculate the should folding probability used in DPF. In other words, inverse folding on should noted structure is a unique strength of our approach. Now I'd like to introduce our future work. We plan to utilize should BPP for other tasks, such as optimizing transcriptional efficiency. And since our model doesn't account for all energies, we are working to expand it into a complete version, including all energy parameters. And we will include the partition function of should-noted structure to calculate the should-noted structure's folding probability. I'd like to thank the following individuals for their valuable discussion and support. That's the end of my presentation. Thank you so much for listening.
Thank you very much. The session is now open for discussion. Is there any question or comment? Okay, I have one question. Your method works fine for the very few of the problems, but many of the cases are not better than the existing method.
Yeah.
So I wonder what was the key factors that
Okay.
the
So
difference was a very good result and
yeah,
was an average result.
yeah.
What do you think?
Yeah, I think the length of sequence is important for this accuracy. And as I said in this slide, our method optimizes the total probability of the structures nearby the target. But the DPF method maximizes this target structures folding probability. So it's it is not our methods cannot outperform
So
this.
you think the RNA size is the most critical point?
Yes.
Uh,
And
your method works better for the shorter ones or longer ones?
yes, shorter ones our method worked well.
Well, I think it's reasonable.
So I think why the length is important is kind of we maximize the nearby as a total probability of sequences, and the sequence structures nearby the target structure are increasing when the length of sequence is large.
Okay, thank you.
Thank you.
Any other questions?